It's difficult to look into the future, especially for energy distribution companies who need to take decisions on investments over the long term, as well as meet the needs of an ever-growing dynamic. Which innovations will be pursued? Which choices will the consumer make? And what regulations have to be taken into consideration? Wouldn't it be useful to possess a tool that scrutinizes various scenarios, as well as illustrating what their effects would be? Something that would be highly beneficial to a company like Liander in its long-term decision-taking. Furthermore, it could also serve as an educative instrument in discussions on the scenarios and their impact with the various parties involved. SmartCap ToolBox 1.0 is a first version of the tool in question. It is an interactive simulation model that can be used widely. The following basic principles have been laid down to enable the SmartCap ToolBox to be put into action across the board. The model has to be able to handle a variety of scenarios. The model has to be simple to use. Several analysts have to be able to work together within one environment, as much as possible compatible with existing tools. Available interactively for a varied public. To cater for all these wishes in the right way, we have opted for a so-called serious game that originates from autonomous objects. The objects, also known as agents, listen to events in the vicinity and give each other signals on the basis of their own internal logic and randomizing. This method of modeling makes the tool incredibly flexible. The model is comprised of 5 basic parts. Generate an environment with the help of objects, in this case the Liander net topology. Then position the objects in the environment that supports the issue. Play the event model and allow all the objects to react to one another. Observe the real-time effects and interact with the model. Collect all data to be able to make analyses outside SmartCap. To make the impact on the energy network visible for Liander, a model has been made of all the connections that come under one high-voltage substation. This also includes the electrical infrastructure of the medium and low voltage. The model allows one to see in clear steps what the result is from its various choices and settings. First off, one sees the present state of the environment. This so-called basic load shows the electric behavior of the environment as it is at present. The environment is topologically an abstract reproduction of the reality. However, the connections conform to Liander's GIS data and asset data. We shall now make adjustments within this environment for situations that could occur in the future. What if we were to add 30% electric cars that could be charged at any given moment from the owner's home? As you can see from the blue cables, the effect of this scenario is considerable. Large sections of the Liander network have not been designed to handle this increase in demand. These blue cables clearly illustrate that the desired capacity is not available. Besides investing in heavier cables, which is a costly business, what other possible scenario could be envisaged to guarantee that everyone could be supplied with electricity in the event of a 30% rise in electric transport? Quite possibly, an idea would be to supply people with a so-called smart device that, on the basis of the energy supply, would coordinate supply and demand intelligently. This smart device would act autonomously within the model and adjust the car's charging performance. In this case, the number of overloaded cables would diminish by roughly half. Instituting the smart device can be one way to absorb the 30% rise in electric transport. The all-round flexibility of the model means we can carry out more tests simultaneously. What if we were to assign a battery to every 10th house, with the capacity to offer support during peak times, while charging itself during the night? As you can see, the overburdened cables diminish even further. In this way, Liander can explore a great many scenarios using the SmartCap ToolBox, and thus have a better insight into the possible options for the future. The setup of the model makes it possible for people with varying backgrounds to work together relatively simply on a scenario. The SmartCap toolbox is built on an existing game engine. Besides the use of C++, most developers and analysts can make use of a visual script language. This makes it relatively easy to modify objects and test new ideas in a model. The visual aspect of the game engine is an important bonus in that it aids communication and the analysis of complex issues. SmartCap Toolbox, an interactive simulation model with its eye on the future.